we're going to start with 1 mole of H2O. And we need some way to convert this from a mole of H2O, which was the info we were given, to figure out how many moles of hydrogen gas are produced. Well, the good news is our reaction up here gives us the ratio. It says that we react 2 moles of H2O, and when we do that, we get 2 moles of H2 gas. Okay? So this is pretty simple math. I'm going to pull out the calculator anyway, just to give myself a little practice with this. But to do this, we can multiply across and then divide by whatever's on the bottom. So 1 times 2 divided by 2. I'm betting that most of you can do this in your head, so you don't have to pause here. But 1 times 2 divided by 2 is 1. So for each mole of H2O we react, we get 1 mole of hydrogen gas and that's good news. That means it's a pretty efficient process. I'm going to circle that answer. And if you're ever on these equations trying to figure out if you did them right, remember the units should cancel out. So we get moles and moles of H2O. We're left with moles of hydrogen gas. Great. All right, so that's good news. This is a fairly efficient process as far as we know. Now, we don't actually know the mechanics of it, but chemically it's efficient. Good. Our next question is, great, we made this gas, but we have to carry it around in the car. So we want to know how many grams of hydrogen gas are we getting. So let's say we split 100 moles of water. So we're going to start with that, or excuse me, 100 grams of water. So we're going to start with 100 grams of water. Oops, that should not say gas. Obviously we'd be splitting liquid water. There's no reason to do this with steam. So let's set this problem up. We have 100 grams of H2O, and we want to see how many grams of hydrogen gas that will produce. Now, this is stoichiometry, ladies and gentlemen. We cannot go grams of H2O to grams of hydrogen gas, and here's why. This equation we use, this chemical equation that translated moles of H2O to moles of H2 for us, it can't do the same thing for grams. These numbers mean moles, okay? So we have to find another way to do that. The good news is we know how to go from grams of H2O to moles of H2O. You learned that when we learned about molar masses. So let's start with that. How many grams of water are in 1 mole of H2O? Well, we've got 2 hydrogen atoms, so those each weigh 1.01 grams. That's the atomic mass of hydrogen. And we've got 1 oxygen atom. Oxygen atoms weigh about 16 grams per mole, so we can add that together. That was calculating molar mass, and you've got to meet that in your notebook on page, wait for it, 84, all the way at the bottom. We already did this calculation. And we figured out that water weighs 18.02 grams per 1 mole. Good, so now we've gone from grams of H2O to moles of H2O. Now we need to go from moles of H2O to moles of H2. We're just sort of one step at a time converting this number into the number we really want. So we know that moles are going to have to be at the bottom. 1 mole of H2O. And we learned up here that 1 mole of H2O produces 1 mole of hydrogen gas, so that's easy. Now we've got moles of hydrogen gas, that's good, but we don't want moles, we want to know how many grams of hydrogen gas are produced. Can we go from moles of hydrogen gas to grams of hydrogen gas? We can. So if you're struggling with these, go ahead and pause it here and take a second to think. All right, let's take a look. We've got moles of hydrogen gas up here. How much does 1 mole of hydrogen gas weigh? Well, that would be another molar mass. We know that we've got 2 hydrogen atoms here. Each hydrogen atom has an atomic mass of 1.01 grams per mole. So H2 should have an atomic mass of 2.02 grams per mole. There we go, ladies and gentlemen, that's a lot of steps, but if you look at our units, these cancel out, these cancel out, these cancel out. We should be left with grams of hydrogen gas, and that's good news. Now, before I do the math on this, I want to tell you, if you're struggling on these, I want you to go back to page 15 and finish up the practices I gave you on these kinds of problems on page 15. That'll give you some good practice. Take a second, pause the video, and see if you can do that calculation. Remember, you're just going to multiply all the way across and then divide by all the things on the bottom. Go ahead and pause. And now here I'm going to show you how I calculated this. Let's see if we get the same answer. So we have 100 grams of H2O. We're going to multiply that by 1 times 2.02. Could you skip the ones? Absolutely. 1 times anything is whatever that thing was, but I'm not skipping them because I don't skip steps. So 202 on top. Now we're going to divide by everything on the bottom. So we're going to do 202 divided by 18.02 divided by 1 divided by 1. Now, could you skip the divided by 1 steps? Absolutely you could. But once again, I don't skip steps because they may not always be ones. So our answer is 11.21 grams of hydrogen gas. Okay. All right. What does this mean for our car? Well, that doesn't sound terribly heavy. That's good. But you have to remember, this is hydrogen gas. So if we're going to carry it around as a gas, the weight matters, but so does the volume. If only your teacher had taught you a way to figure out the volume of gases. Well, she did. Wow, incredible. What a lady. That takes us back to PV equals nRT. Today we are putting all the things you learned this unit together. Now, if you just experienced a small shock, go ahead and pause this video and do a little bit of refreshing on PV equals nRT before we go on. If you're trying to figure out where in your notebook that is, you'll see that on page 70. Go ahead and take a quick look to remember how this works. All right, so this question wants to know, what's the volume of that H2 gas at standard temperature and pressure? Now, standard temperature and pressure means different things in different places, but let's think about what it should mean for our vehicle. What temperature is that vehicle going to operate at? Well, I would say about 70 degrees Fahrenheit, which is about 20 degrees Celsius. Okay, and we know that we have to do PV equals nRT. It always needs to be in Kelvin, so we're going to convert that by doing 20 degrees Celsius plus 273.15, and that will give us our temperature in Kelvin, and that'll be 293.15 K. So we've got our temperature. Good. How about standard pressure? Where are we driving this car? Well, if we're driving in Gainesville, Gainesville is almost exactly at sea level, which means we have a whole Earth's atmosphere above our heads. That means the pressure should be about 1 atmosphere, 1 ATM. Now, unfortunately, this changes if we decide to drive our car up a mountain. This is going to get lower and lower and lower as less and less of that atmosphere is above us, pushing down on us. So this is just going to be an answer for Gainesville. But that's okay, because we're just trying to get a rough estimate here. So let's see what we've got so far. We know our pressure is going to be 1 ATM. We don't know our volume. That's our X. And we know that that is equal to nRT. This is where I'm hoping you'll put some pieces together. N, we learned, means the unit of gas, or units of gas, the amount of gas. I taught you this because I wasn't quite ready to teach you moles. I wanted us to get a little bit more chemistry under our belt first. Maybe that was a mistake, maybe not. But ladies and gentlemen, I want you to know that when we measure the amount of substance, we're measuring the molecules, which means we're measuring this in moles. So now you know this N, the amount of substance, is always measured in moles. Well, how many moles of this do we have? Oh, yikes. Okay. We could go back here and just take off this last chunk and do the math again, and it would give us moles of H2. Okay? Because all the other units cancel out. We could, or we could do one more practice. Doesn't that sound much more fun? Here we go. Let's take our grams of H2 and let's do a little bit of working backward. We have 11.21 grams of H2. We want to convert that to moles, no problem, because we know that 2.02 grams of H2 is equal to 1 mole of H2. We can do that math, and we find out we have 5.55 moles of H2. Awesome. So we're going to plug that in here. I don't know if you can hear the music outside the doors, but it's a good time today. So 5.55 moles. Should we be putting units on this? Yes, but I'm a little short on space. Don't tell my teacher. Now R. What R do we use? Well, if you check page 70, you'll see that if we're using ATMs, which we are, our R is 0.082, and we already did our temperature is 293.15 degrees Kelvin. Let's draw a line here so we don't get these confused. All right, good news, ladies and gentlemen. The rest of it is just plugging into the calculator. So go ahead, pause this, and see if you can solve for x on this. All right, here we go. What I'm going to do is I'm going to multiply these together first, and then I'm going to divide by 1 to leave x on its own, but divided by 1 is really doing nothing, so I'm just going to multiply these together. So we've got 5.55 times 0.082, whoop, I typed it wrong, 5.55 times 0.082 times 293.15. Did I do that right? Yeah, that looks good to me. All right, that gives us 133.41. And volume is always calculated in liters, so let's write that answer down. Volume, oh, I forgot to draw the rest of my arrows. So this is moles, this was our gas constant, this was temperature. So we do all of our math, and our volume turns out to be 133.14 liters of hydrogen gas. Ladies and gentlemen, we have a problem. 133.14 liters is a little more than 62-liter bottles of hydrogen gas. And that's only 11.21 grams of hydrogen. That's not a lot of hydrogen. Do we want to carry around that much gas, like literally like a gas, in our car? No, that would require an enormous fuel tank. So probably what we're going to need to do to make this hydrogen fuel work is we're going to have to either compress it down or chill it down so that it's liquid. Either way, that's going to require some energy. So that's not good news. Speaking of requiring energy, we also want to know, when we split water into hydrogen gas, is this exothermic or endothermic? Here's why we care. If it's exothermic, then we're going to get some energy from this process, and we can use that energy to do other things. But if it's endothermic, it means this process is absorbing energy, meaning it's going to take a lot of energy to make this fuel. Yes, ladies and gentlemen, last thing I promise that we're putting together for today. We've already put together all of our mole calculations, all of our gas laws and kinetic molecular theory. Finally, we are putting together bond energies. So let's figure out if this reaction is exothermic or endothermic. On the reactant side, what kind of bonds do we have? Well, we have OH bonds, because a water molecule is oxygen connected to 2 hydrogens. So this is one OH bond, and this is another OH bond. So we've got how many OH bonds? 2 of them, but there's also 2 molecules of water, so altogether we have 4. Okay, 4 moles times, we can grab our bond energy chart and figure out how much energy it takes to break that bond. Let me take a look. Where's OH on here? There it is. OH is 467 kilojoules per mole. Okay. So we can do that math. Go ahead and pause this, grab your calculator, do the math, or don't. I'm going to give you a chance to do the other side. And we find, alas, 1,868 kilojoules are absorbed for each mole that we produce. Or excuse me, for each mole of water that we break down. Well, this might not be bad news. If this one releases a lot more energy than that, then it might still be an exothermic process. So go ahead, pause the video right here, and try to calculate how much energy is going to be released as these bonds form. Go ahead and pause it, and then I'll show you. All right, here we go. On the energy release side, we've got H2 and O2. And that means we've got two kinds of bonds. HH bond and an O to O bond that's a double bond. How would you know what these are in a test? I would tell you. That is way above the level of chemistry we're at to be able to figure this out. Now, how many of each of these bonds do we have? Well, here, we've got two hydrogen molecules bonded together, so one bond, but there's two of those molecules. So we're going to have two of those bonds, and over here, only one of this bond. Now we check on our chart, and we see that hydrogen releases 432 kilojoules per mole for each bond formed, and oxygen releases 495 kilojoules per mole for each bond formed. When we add those all together, this side plus this side is going to be, if you got this wrong, pause it, try it again. When we add them all together, we're going to get 1,359 kilojoules per mole of energy released. Yeah, folks, this is bad news. So when we do the final math, energy released minus energy absorbed, here's what we get. 1,359 kilojoules per mole minus 1,868 kilojoules per mole. Do that math and we find that for every mole of water we split to produce hydrogen gas, it's going to take 509 kilojoules of energy. I guess this shouldn't surprise us. It takes a lot of energy to harvest gasoline or harvest petroleum from those deep underground oil shafts and then turn it into gasoline. So I guess we shouldn't be surprised that it also takes energy to produce hydrogen fuel. But there we go. Here's what we've learned. We can produce hydrogen fuel through electrolysis. And if the electricity we use to do that is renewable, then this could be a renewable source of energy for vehicles. We know that it's going to produce pretty efficiently 1 mole of H2 gas to 1 mole of H2O. We know that, unfortunately, the gas as a volume is going to be huge, so we probably need to either condense it or chill it until it's a liquid. That's going to require some energy. And we also learned that this process also requires some energy. All right, ladies and gentlemen, that was a lot. Great job.